Hello everyone, my name is Vittorio Ghirardini and I am a member of the Rosita Cluster and Cosmology Working Group, and I'm going to talk to you about cosmological constraints from cluster number counts in the first eRosita All Skies survey. So this talk is about cosmology, which feels a little bit maybe off topic compared to what is the topic of this conference, but there is a connection. So cosmology is about formation and evolution of the universe, particularly how we start from the Big Bang and inflation, which produces minuscule fluctuations, which then grow and evolve and form the very large-scale structure that we know of today, which is made of stars, galaxies, galaxy clusters, filaments, and voids in general. So the friends that I'm going to talk about today, it's galaxy clusters. So galaxy clusters, as the name suggests, are overdensity of galaxies in the galaxy field. So if you count galaxies over the skies, there are some particular regions over the sky where there are more galaxies than in other places. On these places, it was later discovered in the 60s, when the first X-ray telescope were launched, that there is a very hot and diffuse gas that fills all the space in between all of these galaxies. This is depicted quite well in this image here to the right-hand side of your screen of the Coma cluster, where you see all of the galaxies that are member of the cluster. But you also see this fuzzy, bluish, purplish color that is not fully clear. I mean, it's like a very fuzzy that represents that is actually this very hot and diffuse gas that we're able to observe in galaxy in X-ray, especially in this case, it's with XMM Newton, which is an ESA telescope. So galaxy clusters are very massive because they are comprised of a lot of galaxies, tons of galaxies. Their total masses is more than 10 to the 14 solar masses. They're also very hot, which enables the emission of X-ray from Strahlung. They are very large and so on. But what is their relevance for cosmology? So if you take a small patch of Planck CMB maps, where you have these minuscule fluctuations order 10 to the minus 5 between the cold and hot in the hotspot, cold and hotspot. This is a temperature field, and in the early universe, this corresponds basically one-to-one to a density field, like the one you see on the right-hand side in a 1D space. And if you take a region of the space close to one of these peaks in the density field, put that into simulations, let the simulations evolve up to present time or redshift 0, you have formed exactly where you had this peak, this primordial peak, you have formed the galaxy clusters that we know of today. So what this means is the fact that clusters trace the evolution of the density of the peaks in the density fields. And this is very useful in order to do cosmology, because you just need to know how many peaks there are in the present day, or how many clusters there are as function of peak depth, or basically mass nowadays. And basically, you're almost designing the cosmological experiments. And in fact, the quantity that is typically used to connect the two is indeed the Halo mass function, or how many clusters there are in a volume of space, or a function of distance, and as function of mass. This depends on cosmological parameters, and this crowded picture here shows how that depends on the sum of the neutrino species, So in hot colors, you have how Halo mass functions depend on neutrino masses at low redshift, and in cold colors, you have how the same quantity depends on neutrino masses at high redshift. Overall, there is a slightly more effect there at high redshift. However, the important point I want to highlight here is the fact that here I'm changing the neutrino masses from 0 to 1. I mean, there's some from 0 to 1. And you see that as you increase the mass, you decrease the Halo mass function, or you decrease how many clusters you form in the universe, because neutrino smooth out the density field and therefore suppress surface formation. Coming back to our friend galaxy clusters, there are many different and interesting ways in which we can detect and study galaxy clusters. For example, there is optical, which is the traditional method in which galaxy clusters were found. However, the matter that emits in optical represents only 5 to 10% of the matter we can study in the universe, or the baryonic matter. And also, a galaxy cluster are very spectacular in radio because relativistic electrons are accelerated by and then curved by magnetic field, and therefore they emit using synchrotron mechanism and can produce very nice images in radio. For example, you see in LOFAR, for example, radio halos or shocks that are produced by mergers and so on. However, electrons are really tiny square fractions of the visible matter, the baryonic matter in the universe. The vast majority of the matter in galaxy clusters is in this space-filling gas or intercluster medium, which is 85 to 90% of the visible matter in galaxy cluster. This, I was mentioning before, is very hot and it emits X-ray from stellar radiation. So X-ray is a very powerful probe to detect the majority of the visible matter in galaxy clusters. But also we need to remind us that SZ, or Sanyev-Davich effect, is also a very prominent and very powerful way in finding and detecting cluster. And in fact, there are alternative experiments to Rosita, like for example, SPT, that is detecting and studying, doing cosmology with galaxy clusters in the Z. Cool. So eROSITA is an X-ray telescope. I just spoiled that. And it was launched almost 5 years ago and is one of the 2 telescopes on board of SRG, or Spectrum Monitoring Gamma. And in particular, eROSITA is a soft X-ray instrument with a very large field of view, which is capable of scanning large area of the sky efficiently, so quickly. So we are actually doing all sky survey in a relatively decent amount of time. We're able to do 1 all sky survey every 6 months, which is a good rate. And this is how images of clusters look like in actual eROSITA images. So you see there are these fuzzy blobs that becomes a little bit fainter at higher redshift than at low redshift. Importantly, to assess this number on the bottom, the redshift or the distance from us, we have information that comes from the optical. And optical, it's very important because, as you can see here, the clusters at higher and higher redshift become redder and redder, and therefore, thanks to the so-called cosmological redshift effect, we're able to measure the distance of galaxy clusters thanks to the reddening of galaxies in optical. Furthermore, we have dedicated understanding with modern reclancing surveys, which are able to measure the distortion of galaxy shapes behind galaxy clusters and thus infer the potential well that these clusters induce in space-time. We don't have access to the entire sky. We have access only to the Western galactic hemisphere, which is mostly the southern equatorial field, as you can see here. Due to the survey strategy of eROSITA, and not everything is observed uniformly, the regions closest to the south ecliptic pole, which is this white, very bright region that you see there, are way more exposed to the region in the equatorial field, like here. However, we have the Milky Way in the way. So Milky Way is very bright in X-ray, so it's very hard to find clusters behind this bright emission. Furthermore, there is a lot of hydrogen and neutral hydrogen that is present in our galaxy, which is blocking the view, and therefore it's really making the signal from behind galaxy cluster very faint. So only the rest, it's really usable in eRASS1. And also these 2 patches here are the large and small Magellanic Cloud. And these are the locations color-coded by Redshift of all the clusters that we are using for our cosmological inference in eRASS1, which are, yeah. And you see, as expected, that the number density of objects close to the south ecliptic pole down here, it's quite larger than the number of objects in an equatorial field, for example, here, which is of course due to the survey strategy. And furthermore, we have dedicated weak lensing measurements from KITS, DES, and HSC datasets, which enable us to calibrate the mass scales of the cluster population and therefore really connect our observable with cosmology. That is done in particular through the so-called forward model, which is basically how we connect the Helmholtz function, or how many clusters we have as function of cosmological parameter, and observations. This is done basically if you take the Helmholtz function, it's basically an histogram, as was mentioning before. And on this, we have some astrophysical knowledge, which allows us to associate an observable for each mass. We don't observe all of the points here. We only observe a fraction of them because of selection effects, because one might be close to the selection limit. Basically, the detection of clusters tends to be quite some probabilistic at the detection level. And furthermore, we don't have access to the true observable. We have access to a scattered version of it. And here we also have some unknowns. So by marginalizing out the unknowns that we don't know, we get exactly an histogram, which is function of the observed observable. This is in the case of one-dimensional case, but we have multiple dimensions in general. And this is like just an example of two quantities that we have, which are richness, or how many galaxies there are, and the X-ray count rate. And basically, by building up this histogram in n dimension, in our case, we have 4 dimensions. We have richness, count rate, redshift, and the shear profile. We can then build a likelihood by comparing the model to the data and infer cosmological parameters, including the sum of neutrino species. And let's just, so we have also analyzed the standard case where it's just a lambda CDM, so neutrino mass is fixed to 0, which we know it's unphysical, but still we fixed that, we analyzed that case. We also analyzed the case where we have dark energy location of state free to fit, but the most relevant aspect of our research for this, for our purposes today, is regarding the results on neutrino sum. So probably during this meeting, we will hear a lot about current state of the art of neutrino experiment that allow to probe their mass through oscillation experiment or beta decay experiment. There are many different ways in which one can do that, but roughly the value that we take in our paper as some state-of-the-art value for direct neutrino measurement of the masses are the one illustrated here. And in the past, there have been many other indirect experiments that were able to probe the sum of neutrino masses, for example, Planck-SIMB or Planck-SIMB combined with multiple other probes. And one thing that we always need to take into account is the fact that cosmological experiments, like my experiment, like the one the result I'm going to show, depend a lot on the assumption of the model, of the cosmological model behind, while direct observations, like oscillation experiments or beta decay, do not really depend on the cosmological assumption, and therefore, yeah, if you detect, if in the future direct experiment detect a very large neutrino mass, that will have a very big importance, not just physically for neutrino physics, but also at a cosmological point of view, as basically every single cosmological experiment always predict some upper limit on neutrino masses, like on the orders of between 0.1 and 0.2 electron volts. Okay, so this is our results. And for For the viewers which are not familiar, we also show two very common cosmological parameters other than the sum of neutrino masses, which are omega matter, or how much matter there is in the universe, and sigma 8, or which is the RMS in some spheres in the universe. And this is where result lies. So we also produce upper limits on neutrino mass. This is our posterior. And this is how our posterior compares with the result from Planck CMB in all parameter space here. So if you just focus to this bottom right plot here, you see that our constraints are very competitive compared to the CMB results. And indeed, we can go ahead and compare the two and put them together and to provide a single constraint, which is the red curve that you see here. And we get an upper limit, which does not depend on the model. It does not depend if the mass hierarchy is normal or inverted. We get an upper limit is a roughly 0.11 electron volt, which is very close to almost ruling out from a cosmological point of view the inverted mass model. And this is a comparison with recent result from SPT or from SD surveys, as you can see here in the green or in the brown. And so I think I can stop my presentation here. And these were basically the main results coming from neutrinos. But in our paper, we have gone through many different aspects of our analysis. So, for example, possible tension with the lambda CDM that we don't see at the moment, and the fact that our results are in tension with cosmic shear experiments, or that we are really able to measure late-time cosmological parameters like dark energy equation of state, basically fully consistent with the value with -1, which is the value that is inferred and is basically the one that is by default in the lambda CDM cosmological model. So we are fully consistent with the lambda CDM cosmological model at the moment, but we need all to wait for future zeta results, which will going to happen maybe in a couple of years, probably. We will see. That will really be groundbreaking on cosmology, but also maybe also on neutrino physics and constraining the sound masses. Thanks.